Good morning, ladies and gentlemen of AP Statistics. Welcome to class. It's Friday. We have yet another video sub. I think we've now officially set the world record for the number of video subs in a week. I'm actually in the building today, but I'm unable to join you, so we're going to take a look first of all at the quiz that you took yesterday. If you were not here for yesterday's quiz, it's in the test center for you. Please make sure you picked up your copy of your graded quiz over on the table, and let's take a look. Here's one student solution to the quiz. Number one, the arithmetic operation was multiplication, and she multiplied the probabilities together. Number two, she assumed that the events math grade and science grade were independent events. Most of you got that. Now, a mistake on this would be to say, well, they're independent events because they have nothing to do with each other, or basically talking about the idea of disjoint events. But remember, independent and disjoint are not the same thing. In fact, if two events are independent, it's impossible for them to be disjoint. And if two events are disjoint, it's impossible for them to be independent. Let's see how this student responded to this assumption that math grade A in math and A in science are independent. The student said, I do not agree. Students generally have the same study skills and motivation for each of their classes, therefore they are likely to get similar grades in each class. Now, the reason this is a full credit answer is that it recognizes that the probability calculation for getting an A in science is changed once you find out what the person's math grade is. Just like picking a card out of the deck, giving you some information, and checking to see whether that influences your calculation for the other attributes, the probability of the other attributes. So, for example, if you pick a person at random and say, oh, they got an A in math, what's the probability they got an A in science? Well, it's probably a little bit higher once you found out they have an A in math. That's indication that the events A in math and A in science are not independent. So that's why it is a correct answer to say, I do not agree. Continuing on. Next, Part B, she then estimates that she has a 90% chance of getting at least one A in 3 classes. So what did she do? The arithmetic operation is that she added the probabilities. What did she assume about her grades? Well, she had to assume that in order to use the addition rule, she had to assume that they were disjoint events. Do you agree with that assumption? No, you do not agree. When it comes to disjoint, you don't look at probability calculations and whether they change for disjoint. You just look at whether or not they overlap. Is it possible to get an A in math and an A in science? Well, yes, it is. That's the basis on which you would say, I do not agree with that assumption. Now, I realize that if you have questions on the quiz, you'll be able to probably ask fellow group members for help, so you're not dependent on me. Let's flip over to the back side of the quiz. So, number 2, events A and B. Now you know events A and B are independent. That doesn't mean they're disjoint, but it does, in fact, it means they're not disjoint, but it does mean they're independent. And so, this student said, well, if they're independent, then we know that the multiplication rule applies. So the student just wrote down the multiplication rule. The probability of A and B is probability of A times probability of B. We're given the probability of A and B is 0.18. We're given the probability of A is 0.6, so the student solved for the probability of B by taking like 18 divided by 60, or 0.18 divided by 0.6, came out to 0.3. So that was the answer to part A. And then to find the probability of B complement, you simply subtract the probability of B from 1. 1 minus 0.3 is 0.7. Now, down in number 3, events A and B are disjoint. So if you're given one probability and the probability of A or B, you end up subtracting the 0.3 from the 0.7 to get the probability of B is 0.4. And then the answer to part B, the probability of A intersect B. Well, if they're disjoint, if A and B are disjoint, then their intersection is empty. There's no football. And some of you got thrown off by that, but that's why the answer on part B is 0. The probability of being in the intersection is 0 because they're disjoints. So that's how, in fact, this student actually drew a diagram of that. The probability is 0, and look, there's no football. A and B do not overlap because they are disjoints. I had one other student, let's take a look at this. I had one other student on problem 2. This student got the right, or this student obtained the correct answer. However, she ended up doing more work than she had to. However, it is interesting because I'm glad this student did a lot of extra work because it shows a connection to the Titanic example. So, by the way, it is about 6:38 Friday morning right now, just in case you're wondering how all this works. So, what did this student do on problem 2? This is actually pretty cool. Events A and B are independent. Probability of A is 6. So the student filled in the probability of A down here in the margin is 0.6. And the probability of A intersect B is 0.18. That's given here, so she subtracted 18 from 60 to get 42 to fill in this chart. Now, if this is 0.6, that's got to be 0.4. She did the work to find probability of B is 0.3. So then she was able to put B has a probability of 0.3 over in this far right-hand margin. And 18 from 30 is 12. Add these 3 and subtract from 1 to get 0.28. Can fill in the rest. However, if they are independent, then we should be able to use the Unit 1 judgment criteria for determining whether 2 variables are independent, just like we did with the probability of, or checking to see whether survival is independent of class. Back then, when we didn't have as much algebraic sophistication, we said, well, if the distribution of conditional relative frequencies of one variable is the same for all categories of the other variable, which means you could analyze it in columns of conditional relative frequencies or in rows. And if you do that, you can use this student's information to check to see whether that's true. So, for example, you can take, you can take, what's the distribution of conditional relative frequencies? So you could say, what's the probability of B given that you're in the A subuniverse? So you would take 18 divided by 60 to get 0.3, and then take 42 divided by 60 to get 0.7. So the distribution of conditional relative frequencies for B, for all categories of A, both A and A complement, that distribution is 30%, 70%. I wonder what it is for the other category. So if you take 12 divided by 40, you also get 0.3, and 28 divided by 40 is 0.7. So if we were back in Unit 1, we would have handled this differently. And in Unit 1 we have counts, but you can change these 4 numbers to counts by just multiplying them by 100. Just pretend there's 100 people on the ship. 18, 12, 42, and 28. So you can do it that way, or if you do the analysis in rows, you can see that it's a 60-40 distribution for both the B category and the B complement category. So I really do want to connect together some of the ideas that we had about independence in Unit 1 with the more advanced algebraically expressed ideas of independence that we see here in Unit 6. So that's the quiz. Take the quiz with you. We have another quiz on Monday that covers Chapter 15. This was a Chapter 14 quiz. And you'll have a chance to ask me questions on Monday before we take the Chapter 15 quiz. But now let's switch gears. And you should have also picked up homework assignment 6.6, which is graded. So please, let's switch over here to assignment 6.6. All right. I'm back. What happened in assignment 6.6? Number 19, take a look at that one, please. It says eligibility, construct a Venn diagram of the disjoint outcomes. We have the probability of eligibility as statistics, which is 52%. Now, some of you made this similar mistake on the previous assignment, but you had already turned in this one, so you didn't get a chance to correct it. So you might have gotten dinged 2 days in a row. But some of you made the mistake of putting the probability of statistics as 52% in the cookie instead of recognizing that the cookie plus the football together have to add up to 52%. But anyway, that's the way it should be mapped out. You can do like 52 plus 23, subtract the football, or some people just take cookie plus football plus cookie to get the answer at 0.68. Now, their question focuses on the stuff outside the shape that looks like a dividing cell. So 32% was the answer to part A, and 32% are therefore ineligible for bioresearch. Okay, letter B. What's the probability of computer science given statistics? That's not intersect, that's given statistics. Here's where you can think of it as either leaf or over the sum of the leaves, or sometimes we look at this and think of it as leaf divided by upper branch gives you lower branch. But in the context of a Venn diagram, a more helpful mnemonic device for remembering this formula is football divided by shrunken universe, the shrink wrap universe. So football over a shrunken universe. The universe that has shrunk down to the statistics circle. So let's look at that in the diagram. Computer science intersects statistics is the 0.07 football divided by the statistics circle, which is 0.52. Most of you got this one correct, 0.135. Part C, taking the two courses are not disjoint because there's a non-empty football. You can take both. If they were disjoint, then you could not take both. And once again, hopefully by Monday, you will have completely separated in your mind disjoint from independent, because disjoint and independent are disjoint. They're mutually exclusive. They cannot both happen at the same time. Part D, taking the two courses is not independent events. All right, not independent. How are we supposed to test for independence here? Well, there was an example in the companion problems here. But probably the most accessible way to think about it here is just ask yourself, well, let's take a look at the probability of statistics all by itself. And then, what's the probability of having taken a computer science course? And then let's take a look at the probability of taking a computer science course given that you're taking a statistics course. Because if they're really independent, then those two probability calculations should be the same. Well, parts A, B, and C lead you to conclude that the probability of taking a computer science course is 0.23. It's visual, it's in the Venn diagram. The probability of computer science is 0.23. The probability of computer science, given that you're in the statistics circle, is what you did in part B. And so, since the answer to part B is not the same thing as 23%, which if they were independent, then they would have been the same. You can say, no, they are not independent events. The concepts in number 22 were identical to the concepts in the previous problem, so I didn't hold any mistakes in this against you. Double check to make sure you had the right answers, though. The answers that I was looking for on 22A were 0.04 over 0.09. Check your Venn diagrams. Again, some of you made the same mistake of putting the 0.09 here instead of the 0.05, but correct that now if you didn't have it. 0.77 outside the dividing cell shape. So 0.04 over 0.09 is 0.4. Repeating for part A. For part B, it was no. Travel to Mexico and Canada are not disjoint events because the football is not empty. 4% of Americans have been to both countries. Had they been disjoint events, then it would have been 0% have been to both countries. And part C, no, they're not independent events, because if you look at the probability of US residents having been to Canada, that's 18%. But 44.4% of US residents who have been to Mexico have also been to Canada. If travel to the two countries were independent, those percentages would have been the same. And that phrase, if those two events were independent, then those two percentages would have been the same, was a key statement for getting full credit on the previous problem. And finally, go to your last one. Some of you did number 23, problem number 23. In fact, probably about 10% of you did problem 23 instead of problem 33, although that was more in my later classes. I don't know what that is. Maybe you can send me an email if you know why so many of you did problem 23 instead. But, if I were you, if you did 23, I would go back and do 33. You're supposed to set up a tree diagram. If the flight leaves on time, then 95% of the luggage makes the connection. Branch times branch equals leaf. And but the key comparison here for answering the question about are the events independent, that the probability that the luggage makes the connection is actually dependent on whether the flight is on time or not. Look, if the flight's on time, 95% of the luggage makes the connection, whereas if the flight is not on time, only 65% does not make the connection. So apparently, the probability of the luggage making the connection is dependent on whether or not it's on time. In fact, you could look at the overall probability of the luggage making connection by adding these two probabilities. Here's the probability that the luggage makes the connection. 0.14 plus 0.55, it's about 0.7. About 70% of the luggage makes the connection. But what's the probability that the luggage makes a connection given that the flight is on time? Then it's not the same, it's 95%. So there's often more than one way to look at that. By the way, letter B, the probability of luggage is, it looks like they're adding the 15 and the 95. So yeah, that's where they actually had those out. So not only can you say you can justify a claim of non-independence by saying this probability is not the same as that probability, you can also say that this is not equal to that, or you could also argue, well, this is not equal to that. There's more than one way to argue that. You should have a handout that you picked up yesterday called Probability Rules, Part 4 of 4. I'm going to try to sneak a hot dog problem in at the end of this also. If you don't have it, then I believe our live sub is Ms. Finley today, so she'll be able to provide you with the handout for Probability Rules, Part 4 of 4. And by the way, assignment 6.7 is due on Monday. And so let's take a look at this handout. We're going to do the warm-up and then problem 44. We won't have time for the other problem on there. That's fine. We will probably have time for a hot dog question, so have your hot dog sheet out and ready to go so we can make a quick transition to that if it works out. So you are looking at a warm-up. And the warm-up looks like this. It says A, B, and C are disjoint. So it says A, B, and C are disjoint. As a warm-up, write down what you believe the probability of C is going to come out to be in that particular case. All right. When you're done, take a peek up at the board, see if we agree. Okay, if A, B, and C are disjoint, then, and also if they're exhaustive of all possible cases, they're disjoint. I guess you don't really know for sure what P of C is unless you know that they're also exhaustive of all possible cases. That would justify subtracting from 1 to get 0.1. So the probability of C is 0.1. Would you please draw a tree diagram for me where we take a look at disjoint cases A, B, and C. And let's fill in our given information. The probabilities are 0.3, 0.6, and 0.1. Okay, now we have this other event, event D, which either can or cannot occur, or which either does or does not occur after point A. So D, D complement coming out of all three of these. D, D complement, D, and D complement. Now, we have some given information here. It says the probability of D, given that A has occurred, is 0.85. So we'll fill that in right here. The probability of D complement given A has occurred then would have to be, well, you fill that one in on your own. Probability of D given that B has occurred is 0.8. Fill in this branch on your own, please. And then the probability of D given that C has occurred is 0.71. Fill in that one on your own, and then take a peek up here when you're done to see if we agree. Okay, I hope you came up with 0.15, 0.20, and 0.29 for those probabilities. Then there's some problems down below that we have to figure out. Now, I'm not going to ask you to take the time to do this. Just to save time, I'm going to do the branch times branch equals leaf calculations for you. This would be like the probability of A intersect D, or the probability of A and D. When you take branch times branch equals leaf, you get 0.255, 0.045. The third leaf down is 0.480. That's just branch times branch equals leaf. When you do branch times branch equals the fourth leaf, you get 0.120, 0.071, and 0.029 are those leaves. Now, when we want to find the probability of D, we're looking at number 1 down below. I would like you to take out your calculator, if you don't already have it, and calculate the probability of D based on the information that you see in the tree diagram. Go ahead and take about 20 seconds to calculate that. Alrighty, let's see what we got here. Find the probability of D, and I've actually pre-calculated this for you. And when you take a look at the calculation I had before, and by the way, events A, B, and C, it's interesting, there's 3. That's an attempt at a Venn diagram that has 3 circles in it, but A, B, and C are disjoint, so they wouldn't have any overlap in this particular case. So you can just disregard that. Now, what we have here is, for probability of D, you would have to find the probability of A and D plus the probability of B and D plus the probability of C and D. Or in other words, you would have to add up the 3 D leaves. I've got them highlighted in yellow. When you add up those 3 D leaves, you get 0.806. So that's what I'm looking for in terms of the probability of D. Next, I would like you to take a look at number 2, the next warm-up problem. What's the probability of A given D? So take a few moments to study the tree diagram and answer problem number 2. Feel free to use your calculator. A given D. Okay, let's debrief this one. A given D is going to be either just one of these branches, or it's going to be using the leaf divided by the sum of leaves mnemonic device. Now, Had it been, what's the probability of D given A, then, well, here's the probability of D given that A happened, that you just pick it right off the branch, like picking an apple off the tree. However, this is not the probability of D given A, which is 0.85. No, we are looking for the probability of A given that D has occurred. So we have to lean more heavily on the formula for probability of A intersect D. We have to say, okay, for probability A given D, it's the intersection over D. Well, the intersection is the AD leaf. If you study the tree diagram, that's 0.255 divided by probability of D, which happened to be the answer from part 1. So hopefully for number 2, the probability of A given D, 0.255 over 0.806 came out to 0.316. 0.316 is your answer to number 2. And then here's one to see. Yeah, this one might take you a full minute. Try number 3 on your own. What's the probability of B given D complement? You may begin. Now, it's hard for me to judge for sure whether I'm giving you enough time on this, but whether you're finished or not, let's talk through it. The formula says you need to take the B intersect D complement leaf. Let me zoom in on that just a little bit. So, number 3, you take the leaf that has both B and D complement, and then divide it by the sum of all the D complement leaves. So it ends up being 0.120 over that. It looks like a 0.194. And when you go to your calculator with that, the answer to number 3 comes out to be about 0.6186. So, see if I can find my handout again. Okay, so 0.6186. By the way, the probability, just write down a number 4, it's not on your sheet, but write down the probability of D given A. It's almost trivial, it's just picking an apple off the tree, so to speak. It's 0.85. And the probability of D complement given A, just pick it right off the branch, 0.15. Now I want to emphasize that the 6 leaves in the tree diagram could be fit into the 6 cells of this two-way table. So go ahead and fill in on this two-way table grid down here. A, B, C along the top, D and D complement here. I would expect you to figure out how to take those 6 leaves and match them up with these 6 cells. We're not going to do that now. Let's go to our problem on the next page, number 44. Join me there, please. So, read with me in problem number 44. A company manufactures electronic components for home entertainment systems. A company that does that buys electrical connectors from 3 suppliers. The company prefers to use supplier A because only 1% of those connectors prove to be defective, but supplier A can deliver only 70% of the time. And I'm sorry, only 70% of the connectors needed. So the company must also purchase connectors from 2 other suppliers, 20% from supplier B and the rest from supplier C. The rates of defective connectors from B and C are 2% and 4% respectively. You buy one of these components, and when you try to use it, you find that the connector is defective. What is the probability, given that it's defective, your component came from supplier A? Now, my guess is that you can see a lot of connections between our warm-up problem and this problem. Would you please attempt to set up using the letters A, B, C, and D, where D represents defective. Try to set up a tree diagram that takes this information into account. And take out your calculator, and once you get the tree diagram filled in, get ready to calculate the 6 leaves. But first, make sure that you have it set up correctly. So try to set up the tree diagram based on the information. we do need to move if we're going to have time for the hot dog problem. So, here we go. Supplier A delivers 70% of the connectors, 20% of the connectors are delivered by B, 10% by C. Now, of the connectors that are delivered by supplier A, 1% of them are defective, 0.01 then on this branch. D versus D complement would in this context mean not defective. So that's 0.01, 0.99. Now from supplier B, 2% of their connectors are defective, 0.02, 0.98, and down here it's 0.04, 0.96. So once you get that set up, then just do branch times branch for all 6 leaves. Let me give you the answer so you don't have to take time to type all these in. It's 0.007, 0.693, 0.004, 0.196, 0.004 again, and 0.096. So now you have the 6 leaves and we can answer the questions. You buy one of these components. Probably the most challenging part of these problems on the homework will be to express the question in a simplified form, and then to express that simplified form algebraically. So, the simplified form of the answer, or rather the simplified form of the question is, what's the probability of A given that it's defective? We know it's defective. We know the connector is defective. Now what's the probability that it came from A given that it's defective? Your algebraic representation of this would be what's the probability of A slash D. At this point then you jump to the formula. The formula for A given D would be A intersect D, that's the AD leaf, divided by the sum of the D leaves. So this is exactly the sort of calculation that we did in the warm-up. Here's the AD leaf divided by the sum of the leaves. We have our answer, 0.4667. You would then express that as a complete sentence. Now, I believe that the last side of your handout is blank. Would you please turn, I've got to grab my calculator, turn to the blank side of the handout. Now, I'm still here. I'm back. I want to show you how teachers make up questions about whether or not 2 events are independent. So, I'm just going to, I want to give you some insight into how these independence questions are developed. So, on the blank side, let's take a look at something that might even look like a Titanic table. Let's set up A, B, and C as our categories, and then D versus D complement. Now, using our idea of independence from Unit 1, we know that if this variable up here, let's say that this variable is X, and it has 3 categories, A, B, and C. You know, X might be like class. And then Y might be something like survival, you had alive, versus dead in Unit 1. But suppose we want to investigate whether X and Y are independent. They're certainly not disjoint because they're going to have overlaps here, but are X and Y independent? Well, if they are, then the distribution of conditional relative frequencies for X should be the same for all categories of Y. Or the distribution of conditional relative frequencies for Y should be the same for all categories of X. So if I wanted to create a problem where X and Y were independent, one way I could do it is I could plan out the distribution ahead of time. In fact, I think you remember that on Titanic, the distribution of survival was 32% alive, 68% dead. So that, if they were independent, that would have been for first class, second class, here we have third class. We don't have crew here, but the distribution of conditional relative frequencies would have been the same for all categories there. So, if I wanted something like that, I would want to plan it ahead. Let me take this one and pull it over. That's just like your Titanic example as a reference point. Suppose that I wanted to go, let's say 25%, 75%. So suppose I want to create a problem where it's 25, 75 for all three of these. 25, 75, 25, 75. All right, so now I could start making up numbers, some counts, that were, this number is 3 times as much as that one. Like, for example, I could go 10 and 30, and then make up some other number, like maybe 15. 15 times 3 is 45. And then I'll make up some other number for this one, like maybe 7. And 7 times 3 is 21. I just want the distribution of conditional relative frequencies to line up like that for this one. So now, I'm anticipating that, but of course when I give this problem to the students, I don't show them this table. Instead, what students get would be the counts, and coming across here we've got 25, 32 is the count here. Pull these counts across, 75, 85, 95, 96. So how many people are on board this ship, so to speak? 96. We've got 128. And then when we come this way, we've got 28 coming down for the counts, 60 and 40. Sure enough, 128. Now, sometimes though on the test, we don't give you the problem with counts. We give you the problem with 6 percentages in decimal form, where the percentages are not numbers like these, but they are joint probabilities. They're probabilities divided by the 128. So when teachers are making up problems like this, they would be likely, we would be likely to give you the given information as numbers divided by 128. I'm going to show you what those are. 10 divided by 128. So we might say like 0.078. 15 divided by 128 is 0.117. 7 divided by 128 is 0.054. 30 divided by 128 is 0.234. 0.234. 45 divided by 128 is 0.351. And 21 divided by 128 is 0.164. All 6 of these numbers add up to 1, or 100%. But now it's not so clear whether x is independent of y, because you can't see that 25, 75 in here. So what you'd have to do to investigate whether x and y are independent is set up the distribution on the right margin and the lower margin, and you would have to, so add these numbers up. I'm going to say that those add up to A, and these add up to B, lowercase b. These add up to C, D, and E. To investigate whether they're independent, you would have to calculate the distribution of conditional relative frequencies. You could take like 0.78 divided by the total, which would get you back to 0.25. You could take this number divided by C to get 0.75. And then when you do that, you could examine, is the probability of A, which would be the number down here, the probability of A, which by the way would be whatever lowercase c is, the sum of this column, is it equal to the probability of A given D? The probability of A given D is simply 0.78. And so if those two numbers were the same, which they will be since they're independent, then that's how you can justify a claim. Well, that gives you evidence that they're independent. Now it's much easier to use this technique to show non-independence, because if probability of A and the probability of A given D are not the same, then that's the basis on which you say they're not independent. What some of you were doing on the quiz, or in the homework that I gave back today, some of you were saying the probability of A is not the same as the probability of D. You know, this number down here, C, is not the same thing as A, and therefore they're not independent. No, that's a false comparison. To say that this probability, the probability of A, which is C, is not the same thing as the probability of D, which would be this number over here. That's not it. Instead, you must use this comparison, or this type of comparison. Is the probability of A the same as the probability of A given D? That's how you can tell whether they're independent. We don't have time for a hot dog question today, but assignment 6.7 is due on Monday. Have a great weekend. We'll see you then.